Okay, yeah, let's resume the class. Okay, so I've missed something. So here we have talked about this Euler theorem, and then two simple corollary is, first of all, we can argue that this phi function is a multiplicative function, so that phi xy is equal to phi x times phi y, when the GCD of xy is equal to 1. It's very simple. It's because phi xy by this one is equal to x times y times the product of any prime p that divides xy, 1 minus 1 over p, right? Yeah, but they are, but they don't have any common factor. So you can divide the primes that divides xy into two parts. Those are the primes that divide x, and the other are the primes, let's say q, that divides y. Is that okay? Is that okay? And then x together with this, we get phi x. Y together with this, we get phi y. So it is equal to phi x times phi y. Is that okay? Very easy, right? And then the other one is a special case of this one. If the x and y, they are distinct primes, then it is going to be equal to p minus 1 times q minus 1. Phi pq is equal to p minus 1. Is that okay? That's it. Okay. Okay, so we are done with the discussion of this Euler phi function. But now we are going to look at this RSA critical system, and we are going to make use of a lot of things that we have studied before. One is this Euler phi function. The other is the Euclidean algorithm. And then, basically these two things. So first of all, what is a crypto system? Okay, so a crypto system is a way that allows two parties, let's say one is called Alice, and the other party, let's say Bob, to communicate something that is secretly, without other people, without caring any other people, let's say Eve, who is going to intercept your communication. So let's say Alice wants to send a love letter to Bob, okay, but then Eve is around. So when this letter is sent, then Eve will take it out. And then Alice doesn't care if Eve can take this without sending the letter to Bob. Okay, whether it can be transmitted successfully is not the problem. The problem is what is written inside. Okay, maybe it contains some very important information, like on which day that we are going to go to Taipei to have fun. Okay, then maybe Eve is some nasty boss of this Bob, and then we assign job to Bob on that day. So Alice doesn't want Eve to know what is written inside. Okay, is there a way that we can do so? Okay, so in real life, how can we do so? Yeah, not so real. In real life, you send the letter, but somehow, for some reason, you cannot send the letter directly hand in hand. Then one way is like this: you buy a box, very solid treasure box like this. Okay, and then there is a key that can open this box, and then only it's strange. The key should be on this side. Okay. Okay, only Alice and Bob has the key. And then if let's say this box is very solid, Eve cannot open it. So this works. Okay. So Alice opened the box with the key, and then put the letter inside, locked it up, sent it to Bob, and Bob also has the same key, so that Alice and Bob can open the box. These are the two keys in the whole world that can open this box. Okay. So this is one way for doing so. Okay. So this is a scheme called private key scheme. So Alice and Bob has a private key, or shared key. Okay, perhaps I should call it shared key. They share the same key. But then this is not very good. Okay, this is not very good because let's say Bob has another people who wants to send letter to him. Let's say this time this is the David, okay, somehow. Then in that case, Bob will need to maintain a second key, a different key. And if there is a third party that Bob wants to communicate, there will be a new set of keys. So that's not very efficient in terms of how many keys that you are keeping. So in, let's say, in which year? So there is a scheme invented in 1977 by RSA. So there is a new scheme called, new kind of way of sending this message called public key scheme. Okay. So this is developed in 1977 by three persons, Rivers, Shamir, and this Edelman. And then this scheme is so popular nowadays that we call them an RSA scheme. Okay, I will talk about what is RSA soon, but then slightly a few background. Actually, this scheme proposed by RSA is actually known earlier, 1973, by this Ellis and Cox. So, okay, but Ellis and Cox works with this one, the GCHQ, the Government's Communications Headquarters. It's like the CIA in US, but it is in Britain, in UK. So James Bond works in this part. Okay. So they know this scheme, but because they are using that, they are not going to open this scheme to public. They are not telling the others. But RSA, they tell the others. Okay, so later, they also tell people that we are actually using that, a very similar way. So how does RSA work? How does this RSA scheme work? So it's like this. So Bob has something. Bob has something, let's call it as some like special ink, that he tells people, okay, you can buy from the stores. Any department store will have this special ink for me. That is, if you want to write a letter for me, you use this special ink. So this is a special ink for sending messages to Bob. Sending messages to Bob. So this ink is very special. If you write using this ink, then only I can see that. Okay, but this ink is everywhere, so you can use this ink. So if Alice wants to write a letter to Bob, Alice uses this ink to write the letter, and after writing the letter, Bob receives that. Bob can use a special agent, a special thing that can read the ink, so that Bob can read the message that Alice sends properly. Is that okay? But on the other hand, Eve doesn't have a special solution, a special material that can remove the ink or whatever, so that Eve cannot see that. Okay, so this is the high-level way. But in real life, okay, in our communication using computer, what does that use? So Bob actually tells Alice to write his message encoded using a special function. Okay, so Alice, Alice wants to write the letter 3, write the letter 3. So it asks, so what is the value of this function 3? Okay, then you write down the value of function 3 as if you are writing 3. So let's say the next number that Alice wants to send is 5, then you write down function 5, and so on and so forth. So Bob defines such a function. Okay, so everybody knows how to use this function. But then this function has a property that it is believed that nobody can do the reverse. So you see the function value, let's say function of 5. You see the function of 5 is equal to 108. Then it is very difficult to get back to the original value of 5. So computing the inverse, is it called the inverse? Yeah, computing the inverse is assumed to be hard. So, but Bob, on the other hand, he is the one who is designing this function. He knows how to do the reverse procedure. So from 108, he can get back to 5. So this is the idea. Okay? So this scheme is called a public key scheme. It is because any people, not just Alice, David or Irene or whatever, who wants to send things to Bob can use the same special ink, the same function. And then because this function is hard to crack, then any Eve that is in between, when he receives the message, written in this function, then he cannot or she cannot find out what exactly the original is. Okay? And what is this function? Now, this function makes use of modulo arithmetic. Okay? So this is the scheme. So, okay. Okay, the setup scheme. So what is the setup? So Bob needs to prepare for the inc, the function. So Bob needs to do what? Bob chooses 2 primes, distinct primes, 2 primes, P and Q. Is that okay? Step 1. The next step is, so after Bob chooses this prime P and Q, he computes N is equal to P times Q. Is that okay? The product of these 2 numbers. Okay. The next one is Bob selects an integer E. And then this E needs to be co-prime with phi of n. So for some reason, chooses a number. And then the third part is Bob finds an integer D such that E is the inverse of D, or D is the inverse of E, modulo phi n. Okay, so that's it. So this is the setup. And what is the inc? Okay, so the inc, he tells everybody, the inc that he tells everybody is E, the number E, and the number n. Is that okay? Everybody knows the inc. So he uses this inc, everybody knows. Okay, and then what should Alice do? Okay, so after compute this 1, 2, 3, 4, Bob tells everybody. Okay, so tells everyone the value of E and the value of n. So this is what Bob is going to do. Receiver, so the sender. So what Alice do? So Alice is the sender. So let's see how to send, how to do the encryption. We call it an encryption process. So in the encryption process, Alice do what? So let's say Alice wants to send the message C, a number C. And let's say this C is a number between 1 to n. Is that okay? Wants to send a number C to Bob. Then Alice, sorry, not C. C, let's reserve it for the other purpose. Alice wants to send a message M. Okay, so use M for that, sorry. So Alice then computes the number C, and then what is this C? C is equal to M to the power E mod n. And then send it to Bob. Is that okay? Is that okay? And then for the decryption, so hopefully, so what is going to be transmitted? We are going to send C rather than the original message M. Okay, people look at C. Okay, the question is, if I have C, the value of E and the value of N, can I get back to the original M? We assume that this is hard. Okay, and then what Bob does? Okay, Bob is the decryption side. Decryption. So this is called decryption. Decryption is symmetric. So here, Bob wants to get back. So this is his target. So what he does, okay. So he gets the C. He computes M, which is equal to the message C to the power D mod N. And that's the answer. Okay. Okay. So here, we need to figure out, okay, so this is the scheme. And so far, this part is assumed to be hard. The setup is easy, right? The setup is easy. You choose two large primes, usually large primes, okay? You choose two primes, and then find an E and then compute a D. That's it, okay? Once you have that, everybody knows E and N, and then can send the message. And after that, because D and the factorization of N is secret, everybody knows N, but nobody knows which two primes multiply to get N, okay? So this is something that you want to keep as a secret. So that means that people has E and N, it is assumed that they cannot get D. So if they cannot get D and you have the D that is there, then you are the only person who knows this D and can get back C to the power D. And then it turns out that C to the power D is exactly M. So we will find out what is the value of M. Is that okay? So this is the scheme. And then we need to prove why this works. Okay? We need to prove. So what do we need to prove? Why is it secure? Why is it secure? So we assume that it is secure. But we still need to prove that it is correct. So the correct is, if a message M is raised to the power E, and then this whole thing is further raised to the power D, then we can get back M. Is that okay? So we need to prove this thing, and if it is correct, then it's done. So here, so this is the theorem. So for every message M that is in this 1 dot dot N, M to the power E to the power D is going to be equal to M mod N. Is it okay? This is what we need to do. Okay? Good. Okay. So the proof so we have three cases. The case is, let's get the easiest case. Okay. So let's say M is equal to 0. Then done. Right? If M is equal to 0, 0 to the power E is 0, and then 0 to the power D is equal to 0. So 0 is equal to 0, so it's okay. Okay? The second one, let's say the GCD of M and N is equal to 1. Is that okay? Then, nice. GCD of M and N is equal to 1. Okay, so what is property of E and D? So then we have what? We have E times D is equal to 1 mod phi N, right? This is how we choose E and D, right? This is how we choose E and D. So M to the power E to the power D is equal to M to the power some multiple, let's call it K, is it okay? Because E times D is a what? Is a multiple of phi N plus 1, right? So you can write down ED as K times phi N plus 1, right? Okay. So let's still write it as an equal. It's still equal. Right, I just rearrange things a little bit. Is that okay? Is that okay? Yeah, I just rearrange. So m to the 1, I put it here. And the remaining is m to the power k times phi n, right? So it is m to the power phi n to the power k. Is that okay? Okay, then this is equal to 1 to the power k times m. We are talking about modulo n. Euler theorem. M to the power phi n is equal to 1 modulo n. Euler theorem. So change it to 1. 1 to the power k we know, 1. So this is equal to m. Is that okay? Is that okay? Now there is one case that remains.